Welcome to the third session and the third day of Thurne Battery Week. And today we'll be discussing about the active material handling and recycling. And in today's spotlight, we are having Lödige, and we'll be diving into more of the processing of battery masses in Lödige mixes. So, my name is Rolf Sundström. I'm from the Finnish office of Thurne. I'll be your moderator today, and our today's star is Mr. Franz Brinkmann. He's the technical sales representative from Lödige, and he'll be discussing more about the mixing of today's products. So, if you have any questions regarding the Lödige equipment, mixers, reactors, vacuum dryers of the sorts, for Finland, yours truly. For Sweden and Norway, my colleagues Ibrahim Garib. For Denmark, Rafi Malagazadeh, and for Estonia, Latvia, and Lithuania, Andris Putnins. Of course, follow us on the social media, LinkedIn, Facebook, and YouTube. So, without further ado, I beg you my farewell, and I let Franz do the speaking from now on. Thank you.
Okay, today's session is battery masses in combination with mixing equipment. Most of you know, I presume, that when you talk about the manufacture of battery masses, that automatically you begin with the process, which is more or less the clean area, is the preparation of the battery masses prior to application on current collectors, which are then processed on calendars, pressed and dried, and then cut into shape, assembled into cells, and then finally filled with electrolyte, ready to start. Well, Lödige begins way before that, in that our activities are focused on the dry mixing of the lithium battery masses without the addition of any liquids. Yeah, so we are completely upfront of the whole process. Mixing equipment, well, this is what a typical Lödige mixer for battery masses can look like. In this example here, it's a 3,000 liter mixer in total volume. It's used for mixing the NCM, the nickel, cobalt, manganese oxides, together with lithium carbonates or hydroxides, and additives in powder form as are necessary. Why mixing? Well, the masses that are to be put together are of different physical properties. Some are lumpy, there are different proportions, and so on. So you need to mix in advance to get to the actual mixture that is required for your cell production. But for those of you not familiar with mixing, what is mixing actually? Well, mixing, as Wikipedia puts it, is an actual unit operation which involves the manipulation of a heterogeneous system, that's the one on the right, on the left, with the intent of making it more homogeneous. And the ideal situation is the chessboard structure shown on the right, where each particle is exactly next to a different particle, giving you an optimum mix. But this is an ideal situation. And in real life, depending on the formulation, in this case here, we display it by just using colored particles, red and white. You get, looking at the upper row, more or less an uneven mixed state. You have more or less of certain particles in the mixture, and sometimes they're not equally distributed. And this can have an effect on your cell properties and on any property afterwards for a given product. So the idea of using mixing equipment is to get all these particles as homogeneous as possible in real life, but they won't look as in the ideal state, but there can be, as you see here in the bottom, somewhat of a more realistic homogeneous state where it's more or less mixed ideally. Mixing as such involves physical manipulation, as I explained earlier. This means moving one particle from one point to the next and getting this sort of interaction. And this requires energy, this requires force. And by using mixers, you can manipulate these particles to spread out evenly in the complete mixture. And here's an example of how a Lödige mixer functions. It's a horizontal mixing shaft. On it are positioned the mixing tools. We have here a two-component system, black and white beads for simplicity. And this is where the mixing begins. By increasing speed, you get increased fluidization, you get particle movement, three-dimensional particle movement, and thus interaction, interchange of the individual particles, creating a hopefully homogeneous mixture at the end. And after 1 minute of mixing time, we've cut it short here a bit, you will see that the composition is more or less, from an optical point of view, homogeneous. And that's the aim when using mixing equipment for battery masses or for any industry where you need to put components together. In battery masses, up front of what I just showed you at the beginning of the lecture, there's a vast number of steps involved in the production chain, and the Lödige mixers are fairly upfront, positioned here within this red circle. Up front of the mixer is storage and dosing equipment for the individual components. That is here, here, and here. These are all dosed into the mixer. Then the materials are subjected to mixing, which takes a certain amount of time. After the mixing is complete, then they are discharged into downstream equipment. And in this downstream equipment, you get further processing. This means, for instance, filling into trays. And these trays, with their content, are passed through ovens, where the product is subjected to heat treatment. After the heat treatment, they are again discharged and subjected to a milling process. They're subjected to a winnowing or a sifting process. And then lastly, material is subjected to a magnetic separation process, because certain items, certain components are not desired in the final mix. And depending if you have in-house processing or if you have processing on a different location, material is either conveyed to the in-house processing or it is filled in big bags, ready to be transported to the different location where the cell manufacture then actually begins. Coming back to the mixer, here you see the view of a typical batch mixer as such. It has various features. For one, it is positioned, drive and drum are positioned on a common base frame for ease of transportation and ease of installation. You have on the drum dedicated ports for feeding the components, in this case, lithium cobalt or hydroxide. The additives in the main area, because they're relatively minor ingredients. And then you have the main components, the NCM component there. And because filling and discharge requires air displacement, you have venting as such as well. Inspection ports for inspection, cleaning, and maintenance. And then the drive unit, seal support systems, and in some cases, you have a small sampling port if you want to do quality control checks in between, just to verify that your mixing, your ratio of the product formulation is correct or not. These mixers for battery masses have very specific details, because battery masses require certain points to look into, and the main topic is usually preventing contamination by foreign material, which can be part of the machine because the machine is made of metal, and hence we have different features on there. But for one, in the industrial applications, more or less over multitude of years now, 10 years or so, the sizes have established themselves to around between 300 and 3,000 liters. So this seems to be an industrial standard that we observe. And if production capacities need to be increased, then the number of lines are just doubled or increased, but keeping the mixer sizes the same. Having said that, though, we've been approached recently with a request or with requests for even larger mixers, to handle the battery mass. So there is room, there is changes also on the horizon, but for current needs, 3,000 liters seems to be the benchmark. The machines inside are covered with ceramic tiles, a reason I'll talk to you on the latest slide. The mixing elements that you see here, the plowshare tools, and the shafts are covered with either oxide ceramic or with tungsten carbide coating. Battery masses are toxic, so the issue of containment is a very big topic, and hence we have air purge seals, which are there to help contain material inside the machine from the seal area. Likewise, the machine is dust tight with gaskets, static gaskets fitted on each opening. For larger machines, you have sampling doors, and for ease of operation and practicality, all pneumatic elements are put onto a common panel. Why the ceramic linings? Why the coating of all product contact parts? Well, the idea that foreign material gets into the mix to contaminate it is a very big headache for most battery producers. And so the idea is to avoid metal contamination as much as possible. And it goes to the extreme that the contamination has to be avoided in parts per billion. So we're not talking about parts per million, but going to parts per billion. And this means 1 milligram per ton of material of additional exterior contamination has to be avoided. And to give you a size relationship, you compare basically a bull weighing 1,000 kilograms to a mosquito weighing 2 milligrams. So again, the mosquito on the back of the cow is already over the allowed limit for contamination with iron. How do we prevent metal contamination? Because the mixer is inadvertently made from metal. Well, we coat the surfaces. And for the drum, it has been established over the years now, testing different methods of coating, that ceramic lining seems to be currently the best option. And yeah, the interior looks like bathroom tiles, small tiles which are cemented into place, and these small tiles allow you to follow the curvature of the mixing drum, because different sizes, you have different curvature of the mixing drum, so you have to adapt. And 20 millimeters side length seems to be ideal for this. And the material is cemented into place, giving a good fit into there. But having covered the mixing drum with the ceramic lining only covers 75% of what is in contact with the product. The remaining 25 is made up of the mixing elements, the shaft, and the high-speed chopper units, which are also incorporated into the machine to help distribute the individual components in the overall mixture. And okay, here we've looked into and have used different methods of coating. In the beginning, also, we looked at, okay, if the drum can be coated with ceramics, then potentially also the mixing tools can be coated with a ceramic layer. Unfortunately, tiling a complicated tool like the plowshare is not really a good idea. Very difficult to keep the contour and to keep the tiles in place. So we found basically aluminium oxide coating, plasma welded application, allowing for a very thin layer of 0.5 millimeters, thus giving enough practicality to cover the mixing tools and keep the contour. This coating is good. It's very hard, but it has one drawback, that it's brittle. And the reason it's a drawback is that you can never prevent foreign bodies like nuts, bolts, whatever, large objects, from coming into the mixer together with the raw material. And if this happens and the mixing action is there, and if these foreign objects hit the mixing tool, then if the coating is brittle, you get chances that the coating will split off and you will see the underlying metal coating. Again, this will provide a location for contamination. So we've looked into other various options, and one option is to apply a tungsten carbide coating, which is basically 60% tungsten carbide embedded in a nickel matrix. And this again allows you, with the plasma welding, to apply a very thin layer to follow the contours of the mixing tool. And the one big advantage of this coating is that it's ductile. It's ductile, so the impact of foreign bodies cracking or breaking of the coating is severely reduced. And this helps then to prevent metal contamination from getting into the product. Looking at, because once you start looking into areas where potential contamination can be in mixing, then you look at each individual item in turn. And again, over the course of 10 years, and you can see here, the left and the right picture are machines which are around 10 years apart. And on the left side, you see that here only the mixing drum and the mixing elements were coated, and the mixing shaft was untreated because, of course, the areas of most abrasion were deemed to be the mixing drum, where the material rubs against it, and the mixing tools, which plunge into the product and basically move the product and are subjected to friction and abrasion. But the mixing shaft, being in the center of the machine, was deemed to be not so dramatic for this, because it moves with relatively small tip speeds, and hence friction and abrasion were deemed limited. But nevertheless, customers, they look and they also see where can items be optimized, and say, you have one item still left uncovered in your machine. And hence this led to also the mixing shaft being covered, but in this case, not with ceramics, but with the tungsten carbide coating, giving it a ductile, flexible layer on the mixing shaft, because mixing shafts, although being solid, they do have some form of displaying flexibility. So this seemed to be ideal also to cover this area of the mixer. Another area that needed to be looked into when handling battery masses was the high-speed choppers. And these are items which are auxiliary items and are fitted in the area of the drum where the product density is the highest. So having said that, this is the area where most friction occurs, where they do their work. So these blades are again subject to wear. And in the early days of battery mixing, where contamination was to be prevented by preventing erosion of these items, was to protect the blades with the tungsten carbide metal coating. But unfortunately, during operation, these items are subject to wear. But practical everyday operation, you don't always get to change or exchange these blades in a timely manner, because people operate 24/7 and production is not allowed to stop. So these blades get worn. Unfortunately, they wear, the coating disappears, and again, the metal comes to the surface and contaminates the mix. So this was not an ideal situation, because one could not take into account that operators would always change these blades in a timely manner. So alternatives were sought. And one idea was to make the blades from the actual materials which are abrasion resistant, but do not contaminate the mix. And this was then that the blades were made either of ceramic, so it's very hard, or the blades were made from the tungsten carbide material. Again, very hard, very, very abrasion resistant. And being that the chopper blades operate with 28 meters per second tip speed, this seemed to be a very good option. And this is sort of more or less established itself as one of the key features apart from coating the mixing elements and the shaft or the drum. This has also been something which has established itself in key features of a mixer. But again, the more you look, the more you see details and the more you see areas where potential contamination can occur. And you can see that mixing not only involves the mixing process, but it also involves side issues which you have to deal with. And yeah, focus today is on contamination prevention. And then customers were looking at, hey, we have here a seal. It's air purged. It's good. Air purging keeps material inside the mixer. There's no escape of toxic material via the shaft seals and amassing in a heap next to the mixer. But what about the air going into it? How is it treated? Where does it come from? Yeah? And so here again, we looked into this, and for one, we changed the design of the shaft seal to a smaller version, allowing us to use again standardized bearing housings, because with other seals, air purge seals available, the bearing housings had to be specially adapted to this, meaning welded constructions, meaning an expensive design. So by reducing everything, we could fall back in this case onto a standard design available on the market. But this is going back to standard. But if you look at how the air is treated, okay, you have an air control system where incoming air is reduced in pressure for the seals, the airflow rate is regulated, and so on. But standardized items appeared to have metals or materials which are absolutely not allowed in battery masses, and this is copper and zinc. So if minor amounts of iron are allowed, copper and zinc are an absolute no-go. So we had to redo again also the air service system, ending up with making everything all stainless steel or polymer based. And again, this is something, a key feature when looking into mixing equipment, is looking into the auxiliaries, and this air treatment is one of them. That was the first mixer. The battery mass production, as I say, has various steps. And up front, there is a mixing step where you have high-speed mixing using plowshare mixing equipment, relatively intensive mixing. But then downstream, you also have another step where mixing equipment or blending equipment is employed. And this is after the magnetic separation. Reason being is that during the course of the post-treatment after the first mixing step, you do get fluctuations in product qualities, physical, that you can negate and equalize by using a post-blending step after the final magnetic separation. The emphasis on the mixing is not that important as in the initial phases, where you have all the individual particles, different physical characteristics. Here, it's more a post-blending. So the mixing is slower, it's much gentler, but nevertheless, in terms of contamination prevention, there you have still the high standards. So I'll just give you an insight as to how these machines look like. Again, they have key features, one being the size. Okay, if you're using mixing equipment up front of 3,000 to 4,000 liters, then the post-mixing uses more or less the same size as well. Mixing action is slow, so here ribbon blenders or paddle mixers have established themselves for this type of duty, giving a much gentler mixing over time. The emphasis on preventing of contamination, again, shows that we have to use some form of coating of all the product contact parts. In this case, we could use a polymer coating because the mixing action is not so intensive. Hence, polymer coating, in this case, polyurethane, was deemed appropriate for the task. For the mixing tools, we opted for tungsten carbide still because the intensity was still so much that polyurethane was not deemed to be that good. The shaft was coated again with polyurethane air purge seals for keeping the toxic material inside, and again, all pneumatic elements positioned on a panel. Having said that, here's a typical view of a ribbon blender in this case. It's very nicely colored. So color scheme on the outside is as customer desires, but you can see here, the mixing shaft is coated with a polyurethane coating. The drum is coated again with an orange layer of polyurethane, but the mixing tools, in this case, the ribbon, has the more ductile and also temperature resistant tungsten carbide coating. Fastening bolts, because they are in the shadow of the mixing process, are deemed uncritical. So they are left untreated. And here again is a picture of the counterpart. It is a paddle mixer. You can see from a design point of view, individual paddles are far easier to fabricate than the complicated ribbon structure. Both items mix and blend equally, so customers can either choose the ribbon or the paddle, or even have a mixture of both, depends how they want to do maintenance, cleaning, and inspection. But here, again, emphasis is put upon the coatings. Again, polyurethane coating on the drum and on the mixing shaft, and tungsten carbide on the mixing tools, and the bolts in the shadow of the mixing processes are left untreated as before, because they don't really get that much into contact with the product. So having said that, this was a more or less brief introduction into mixing of the battery masses. And you can see it's not the only actual physical mixing of the product, getting a good mix, which is then suitable for post-treatment, but you also have to deal with side issues, and the side issues mainly being the contamination of foreign bodies or coming in, or from abrasion, and thus the effects of metal contamination coming inside, or even selecting suitable material components for the auxiliary equipment. And all this is more or less been developed over the course of 10 years approximately, in that we have been delivering these type of mixers, not only for the lithium-ion batteries, but also for other types of batteries in this very interesting field of industry. And with that, I come to the end of my small lecture.